Imagine a planet where battery acid rains down, where air pressure is 90 times greater than on Earth, and where a day lasts longer than an entire year. This terrible place is Venus, our closest planetary neighbor. For years, NASA studied this space hell from afar, thinking they knew all its secrets. But recently, when analyzing the thick clouds covering the planet, they discovered something that made scientists stop everything they were doing. Phosphine molecules, a gas that on Earth only appears in two places: chemical factories and inside living beings. Most shocking is that these molecules are floating exactly in the cloud zone where temperature and pressure are similar to Earth. How did this impossible gas get there? Could Venus, the planet we thought was dead, actually be hiding science's greatest secret? Subscribe to the channel, leave your like, and comment what part of the world you're watching from. Get comfortable and relax. Let's begin. Have you ever imagined that we could find life in one of the most inhospitable places in the solar system? In 2020, a surprising discovery shook the scientific community when astronomers announced the detection of a very peculiar gas in the clouds of Venus. This gas, called phosphine, reignited intense debates about the possibility of extraterrestrial life on our planetary neighbor. The story of this discovery began when an international team of scientists, using the James Clerk Maxwell radio telescopes in Hawaii and ALMA in Chile, detected the chemical signature of phosphine in the Venusian atmosphere. This finding caused great excitement because, on Earth, phosphine is mainly produced in two ways: through industrial processes created by humans or by microorganisms living in oxygen-free environments, such as swamps or animal intestines. What makes this discovery so revolutionary is the fact that scientists cannot explain the presence of this gas through known geological or chemical processes. On Earth, when we find phosphine in natural environments, it is generally associated with the activity of anaerobic microorganisms, those that don't need oxygen to survive. This association raised an intriguing hypothesis. Could microbial life exist in the clouds of Venus? It's important to understand the context of Venus to appreciate how surprising this discovery is. The planet's surface is a true inferno, with temperatures reaching 462 degrees Celsius, 864 degrees Fahrenheit, atmospheric pressure 90 times greater than Earth's, and an atmosphere composed mostly of carbon dioxide with clouds of sulfuric acid. These extreme conditions made Venus an unlikely candidate in the search for extraterrestrial life for decades. However, scientists already knew that in the middle layers of the Venusian atmosphere, approximately 50 to 60 kilometers, 31 to 37 miles above the surface, conditions are surprisingly milder. At these altitudes, temperature and pressure are relatively similar to those found on Earth. It was exactly in these layers that phosphine was detected in concentrations of approximately 20 parts per billion. The quantity may seem small, but it's significantly higher than scientists would expect to find if phosphine were produced only by known chemical processes. In the Venusian atmosphere, ultraviolet radiation from the sun and highly reactive components should rapidly destroy phosphine molecules. The fact that the gas persists suggests that something is continuously producing it. Researchers carefully considered various non-biological possibilities. They examined whether phosphine could be created by lightning, volcanic activity, chemical reactions on the surface, or even by incoming meteorites. After extensive analyses and modeling, none of these processes seemed capable of explaining the amount of phosphine observed. This does not automatically mean that life exists on Venus. Science progresses through skepticism and verification, and researchers are the first to recognize that there are still many unanswered questions. There could be geochemical processes on Venus that we don't fully understand. The very detection of phosphine needed to be confirmed and re-examined by multiple independent teams. In fact, after the initial announcement, some astronomers questioned the data, suggesting that the detected signal could be noise or another molecule with a similar spectral signature. This healthy scientific debate led to revisions of the original data and the conduct of new observations. In subsequent analyses, some teams couldn't detect phosphine at the levels initially reported, while others confirmed its presence, albeit in lower concentrations. This discrepancy can be explained by several factors, including differences in the instruments used, analysis methods, or even real temporal variations in the concentration of phosphine in the Venusian clouds. If microbial life really exists on Venus, how could it survive in such a hostile environment? Venusian clouds are composed mainly of sulfuric acid, with acidity levels that would destroy any known life form on Earth. However, some scientists theorize that microorganisms could have evolved extraordinary protection mechanisms. A fascinating possibility is that these hypothetical life forms could inhabit small water droplets in the clouds, where they would be relatively protected from the surrounding acid. Another theory suggests that the microorganisms themselves could have evolved cell membranes capable of resisting extreme acidity, perhaps incorporating sulfur compounds into their structures. Scientist Sanjay Limai from the University of Wisconsin-Madison observed that some of the mysterious dark particles observed in Venusian clouds have sizes and shapes similar to microorganisms in our Earth's atmosphere. These particles absorb ultraviolet light in a way similar to some terrestrial microorganisms that have developed protection against solar radiation. To really confirm or refute the hypothesis of life on Venus, we need new space missions specifically designed to investigate this question. NASA and other space agencies have already begun planning future missions that could collect samples from Venusian clouds or perform more detailed in situ analyses. One of these promising missions is Da Vinci Plus, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging Plus, which will launch a probe that will plunge through the Venusian atmosphere, collecting precise data about its chemical composition. Another mission, Veritas, Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy, will use radar technology to map Venus's surface and study its geology, which could provide clues about possible non-biological sources of phosphine. European and Asian space agencies are also considering missions to Venus, creating a renaissance in interest in this planet that has been relatively neglected in recent decades in favor of Mars. It's important to note that even if we don't find life on Venus, the search itself is already generating valuable scientific advances. The discovery of phosphine forces us to refine our techniques for detecting biomarkers and to re-evaluate which environments can be considered habitable. This research also has implications for astrobiology and the search for life on exoplanets. If life forms can exist in the extreme conditions of Venusian clouds, this would significantly expand the so-called habitable zone around other stars, increasing the number of worlds where we could potentially find life. The story of Venus also offers lessons about climate change. It's believed that Venus was once very similar to Earth, possibly with oceans of liquid water. An uncontrolled greenhouse effect transformed it into the infernal world we know today. Understanding this transformation can provide insights about Earth's future under global warming conditions. For scientists studying the origin of life, Venus presents another intriguing scenario. If we find life in Venusian clouds, we would have to determine whether it arose independently or if it shares a common origin with terrestrial life. Some researchers theorize that asteroids could have transferred biological material between primitive planets, a process known as panspermia. The discovery of phosphine on Venus reminds us that science frequently surprises us. A few decades ago, the idea of searching for life on Venus would have been considered absurd. Now, it's a legitimate and exciting field of research. While we wait for more data and future missions, the possibility of life in the acidic clouds of Venus continues to capture our imagination. If confirmed, it would be one of the most profound discoveries in the history of science, demonstrating that life can arise and persist in conditions we considered impossible. This discovery also reminds us of the importance of keeping an open mind in our scientific explorations. Sometimes, the most unlikely places can hold the most surprising secrets. Venus, a planet often overshadowed by the fascination with Mars, may end up being the first place beyond Earth where we find evidence of extraterrestrial life. The journey to understand Venusian phosphine and its implications has only begun. In the coming years, new observations, laboratory experiments, and space missions will help us unravel this cosmic mystery. Whatever the outcome, this investigation promises to expand our horizons and deepen our understanding of life and its place in the universe. While the question of phosphine continues to be investigated, scientists from NASA and other space agencies have been intensely studying the general composition of Venusian clouds, which goes far beyond this single compound. These clouds are, without a doubt, one of the most hostile and chemically complex environments in the solar system, forming a natural laboratory of extreme chemical reactions that challenge our current scientific understanding. The first thing we need to understand about Venus's clouds is their basic composition. Unlike Earth's clouds formed mainly by water droplets, Venusian clouds are composed mostly of sulfuric acid in extremely high concentrations, reaching 85% in some layers. To get an idea of how corrosive this is, we're talking about an acid capable of dissolving metal and causing immediate severe burns to organic tissues. This extreme acidic environment makes any discussion about possible microbial life that we mentioned earlier even more surprising. The probes that have visited Venus since the 1970s have revealed to us that these clouds are not uniform in their composition. They form different layers that extend from about 45 to 70 kilometers, 28 to 43 miles, above the planet's surface. Each of these layers has distinct chemical characteristics, as if they were different floors of a gigantic chemical building. In the lowest cloud layer, at approximately 48 kilometers, 30 miles altitude, we find the highest concentrations of sulfuric acid, along with various sulfur and chlorine compounds. This region is particularly hostile due to the combination of high acidity and still relatively elevated temperatures. As we rise to the middle layers, about 55 kilometers, 34 miles above the surface, the composition begins to become even more intriguing. It's here that spectral instruments aboard probes like the European Space Agency's Venus Express detected particles with puzzling chemical properties. These particles, with sizes varying between 1 to 3 micrometers, show ultraviolet light absorption capabilities that don't correspond to any known chemical compound of sulfur or other expected elements. Scientists have nicknamed these enigmatic particles unknown absorbers due to their ability to absorb almost all the ultraviolet radiation that reaches the planet. For decades, it was believed that these particles were composed mainly of sulfur, but more recent observations suggest something more complex. Some researchers propose they might be iron compounds such as ferric chloride, while others suggest they could be complex organic compounds or even particles with some relationship to biological processes. A particularly interesting discovery came from advanced spectroscopy performed by NASA, which identified significant variations in cloud chemistry throughout the Venusian day. During the day on Venus, which lasts approximately 117 Earth days, certain photochemical reactions, chemical reactions activated by sunlight, seem to occur in the upper layers of the clouds, generating compounds that aren't present during the Venusian night. This day-night dynamic suggests an extremely active and complex chemical system, which may explain some of the anomalies observed in the composition of the clouds. In particular, the sulfur cycles in Venusian clouds seem to follow patterns that cannot be easily explained by conventional chemical models. One of the most puzzling aspects of Venusian cloud chemistry is the presence of compounds that, according to our current understanding of chemistry, shouldn't exist in such conditions. For example, spectroscopic analyses have detected traces of water in the clouds, which is surprising considering the extremely acidic environment and high temperatures that should quickly convert any water into other compounds. Additionally, NASA has identified an intriguing chemical mixture in the middle clouds that includes sulfur dioxide, carbon monoxide, water vapor, and sulfuric acid in proportions that suggest some kind of unknown buffer mechanism. A buffer system, in chemistry, refers to substances that keep the pH, acidity level, relatively stable, even when new acidic or basic substances are added to the system. This chemical stability is particularly intriguing because it suggests a system in dynamic equilibrium, something we normally wouldn't expect in such an extreme environment. Some scientists speculate that there could be unknown biogeochemical cycles occurring in the Venusian clouds, similar to the carbon, nitrogen, or sulfur cycles on Earth, where microorganisms play fundamental roles. In 2016, a study published by researchers from the University of Wisconsin-Madison suggested that some of the particles observed in Venusian clouds have sizes and shapes similar to certain terrestrial microorganisms. These scientists proposed that the peculiar optical properties of these particles, especially their ability to absorb ultraviolet light, could be comparable to adaptations developed by terrestrial microorganisms to protect themselves from harmful solar radiation. It's important to note that this hypothesis is not widely accepted by the scientific community, and many researchers prefer non-biological explanations for the unusual properties of particles in Venusian clouds. However, these observations have stimulated new investigations into the complex chemistry of the clouds. Another fascinating aspect of the composition of Venusian clouds is how they interact with the planet's surface. Evidence suggests there is a continuous cycle of materials between the extremely hot surface and the clouds. Volatile compounds, including sulfur compounds, are vaporized on the scorching surface and rise to the higher layers of the atmosphere, where they eventually incorporate into the clouds. This vertical transport of material creates a dynamic chemical system where the composition of the clouds is directly linked to geological processes on the surface. For example, evidence of recent volcanic activity on Venus, observed by the Venus Express probe, suggests that volcanic eruptions periodically inject new compounds into the atmosphere, altering the chemistry of the clouds. NASA researchers discovered that the Venusian cloud layers also contain traces of hydrochloric acid, hydrofluoric acid, and hydrogen sulfide, creating an extremely corrosive chemical cocktail. This acidic mixture, combined with high temperatures, explains why probes that tried to pass through Venus's clouds had such limited durability, a few hours at most, before their instruments were corroded and ceased to function. A study published in 2019 in the journal Nature Astronomy identified iron compounds in Venusian clouds, including iron 3 chloride and iron 3 sulfate. These compounds could explain some of the mysterious optical properties of the clouds, particularly their ability to absorb ultraviolet light. Interestingly, these same iron compounds could potentially serve as an energy source for hypothetical microorganisms through oxidation-reduction reactions, similar to certain terrestrial microorganisms that use iron in their metabolism. One of the most recent discoveries about the chemistry of Venusian clouds came from spectroscopic observations that detected traces of carbonyl sulfide, a compound that on Earth is frequently associated with biological activity, although it can also be produced by volcanic processes. The presence of this compound adds another layer of complexity to the chemical puzzle of Venusian clouds. Scientists have also observed that chemical reactions in Venusian clouds occur at different rates than predicted by theoretical models. This suggests there may be unknown catalysts present, substances that accelerate chemical reactions without being consumed in the process. On Earth, biological enzymes frequently act as catalysts, but on Venus, these catalysts could be minerals or inorganic compounds with properties not yet fully understood. The upper layers of Venusian clouds, located approximately 70 kilometers, 43 miles above the surface, contain smaller particles and lower concentrations of sulfuric acid. At these altitudes, intense solar radiation triggers complex photochemical reactions, creating compounds that eventually descend to lower layers of the atmosphere or are decomposed by ultraviolet radiation itself. A particularly intriguing aspect of Venusian atmospheric chemistry is the sulfur dioxide cycle. This compound should be rapidly converted to sulfuric acid by the conditions in the clouds, but observations show consistently higher levels than models predict. This suggests there is some process that continuously replenishes sulfur dioxide in the atmosphere, possibly related to volcanic activity or unknown chemical reactions. To truly advance our understanding of the complex chemistry of Venusian clouds, we need dedicated space missions that can collect samples directly and analyze them with more sophisticated instruments than those sent previously. The next generation of missions to Venus, including those planned by NASA, ESA, and other space agencies, will be equipped with instruments specifically designed to unravel the chemical mysteries of the clouds. These future missions may finally answer questions that have persisted for decades about the exact composition of Venusian clouds, the nature of the unknown absorbers, and whether there are truly unknown chemical or possibly biological processes occurring in this extreme environment. The enigmatic chemical composition of Venus's clouds continues to challenge our knowledge and stimulate new hypotheses and investigations. Each new discovery seems to add more layers of complexity to this extraordinary chemical system, making it one of the most intriguing environments in our solar system for future studies. Among all the intriguing chemical characteristics of Venusian clouds, there is a specific visual phenomenon that has left scientists particularly perplexed. When we observe Venus through telescopes equipped with ultraviolet filters, we can see something truly extraordinary. Extensive dark spots and bands that stand out against the rest of the clouds. These mysterious regions, formerly known as unknown UV absorbers, represent one of the most persistent enigmas in Venus exploration. These dark zones were first observed in the 1920s, when astronomers noticed contrast patterns in Venusian clouds. However, it was only with the advent of space ultraviolet photography that we could truly appreciate the extent and dynamic behavior of these patterns. What makes these structures so intriguing is that they absorb approximately half of the solar ultraviolet energy that reaches the planet. An enormous amount that significantly affects Venus's energy balance. When the first Mariner probes flew by Venus in the 1960s, their cameras captured detailed images of these dark zones. Later, NASA's Pioneer Venus missions and the European Space Agency's Venus Express provided long-term observations that revealed the truly peculiar behavior of these structures. Scientists discovered that these UV-absorbing regions are not static. They constantly change shape, size, and intensity over time. The most perplexing aspect of these dark zones is their apparently independent movement from the dominant wind patterns. Venus's upper atmosphere is characterized by extremely strong winds that blow at speeds of approximately 360 kilometers, 224 miles per hour, circling the planet in just 4 Earth days. It would be logical to expect that any structures in the clouds would simply be dragged along by these winds. However, detailed observations have shown that the dark zones frequently move at different speeds than the surrounding winds, sometimes faster, sometimes slower, and occasionally even in slightly different directions. This almost autonomous behavior has led some scientists to compare these regions to independent entities within the Venusian atmosphere. In 2016, a team of researchers led by Sanjay Limaye from the University of Wisconsin-Madison published a study proposing a bold hypothesis. These dark zones could potentially harbor airborne microbial communities. To better understand this hypothesis, we need to consider what could be causing the ultraviolet radiation absorption. Spectroscopic analyses suggest that the compounds responsible for this absorption could include elemental sulfur, chlorine dioxide, iron compounds such as ferric chloride, or even complex organic molecules. Each of these possibilities has its own scientific implications. If they are sulfur compounds, this could indicate complex chemical cycles in the clouds that we don't fully understand. The iron compounds theory gained strength when the Venus Express probe detected signs of ferric compounds in the same regions where the dark zones are most prominent. These iron compounds could explain not only the UV absorption but also the peculiar movement, since particles containing iron could be influenced by Venus's weak magnetic field, in addition to wind patterns. The most controversial hypothesis, however, involves the possibility of complex organic materials or even microorganisms. On Earth, various species of microbes, especially certain types of bacteria and algae, produce pigments that absorb ultraviolet radiation as a protection mechanism. These molecules, such as melanin or carotenoids, have spectral signatures that share some similarities with what we observe in the Venusian dark zones. Proponents of this hypothesis point to another intriguing behavior of the dark zones. They demonstrate cycles of growth and decline that superficially resemble patterns of microbial proliferation. Long-term observations show that these regions can expand rapidly over days or weeks, then decrease in a pattern that could be compared to the population growth of microorganisms. A study published in the journal Astrobiology in 2018 highlighted that some of these dark zones seem to regenerate after being disturbed by atmospheric events, showing a type of resilience that would be difficult to explain through just passive chemical processes. This behavior suggests a system that can actively respond to environmental changes. Another fascinating aspect is the non-random distribution of these absorbing regions. They tend to concentrate in specific zones of the Venusian atmosphere, particularly at altitudes between 50 and 60 kilometers, 31 and 37 miles, above the surface. Coincidentally, the same region where temperature and pressure are closest to Earth conditions. At these altitudes, temperatures range between 0 and 50 degrees Celsius, 32 and 122 degrees Fahrenheit, and the pressure is similar to that of Earth's surface. The concentration of these dark zones in regions with specific environmental conditions could suggest that they are formed by processes that depend on parameters such as temperature, pressure, or specific chemical composition. If they are of biological origin, this would make sense. Organisms tend to thrive in specific environmental niches. The Japanese Akatsuki mission, which currently orbits Venus, has provided some of the most detailed observations of these dark zones. Its instruments detected Y or PSI-shaped structures within the UV-absorbing regions, which persist for days or weeks. These distinct formations are difficult to explain through simple atmospheric mixing processes and suggest organized patterns of some kind. In 2021, observations from Akatsuki revealed something even more surprising. Some of the dark zones seem to have a diurnal cycle, becoming more prominent during the Venusian day and diminishing during the night. This indicates a possible relationship with solar radiation, perhaps through photochemical reactions or, if we consider the biological hypothesis, organisms that respond to light availability. NASA scientists have used advanced computer models to try to replicate the behavior of these dark zones. A 2019 study led by Yeonju Lee from the Planetary Science Institute in Berlin analyzed data from 4 decades of Venus observations and discovered that UV absorption in Venusian clouds varies over time in a way that cannot be easily explained by conventional climate models. The absorption patterns seem to follow long-term cycles, with increases and decreases over periods of years or even decades. Curiously, some of these cycles seem to correlate with variations in the speed of Venus's atmospheric rotation, suggesting a complex connection with the planet's global atmospheric dynamics. To further investigate these dark zones, NASA and other space agencies are developing new instruments capable of analyzing the chemical composition of Venusian clouds with unprecedented precision. The next generation of spectrometers will be able to identify specific compounds in the UV-absorbing zones, potentially resolving the mystery of their composition. A particularly promising instrument is the mass spectrometer, which could identify complex organic molecules or specific biomarkers if these are present. Future missions to Venus, such as NASA's Da Vinci Plus Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging Plus, will include such instruments in their payloads. Another investigative approach involves the use of atmospheric balloons or gliders that could float in the middle layers of the Venusian atmosphere, precisely where these dark zones are most prevalent. These atmospheric vehicles could collect samples directly from the UV-absorbing regions for detailed analysis. Russia and the European Space Agency have already demonstrated the viability of this approach with the Vega balloons in 1985, which successfully operated in the Venusian atmosphere for more than 46 hours. Modern technologies would allow much longer duration balloon missions, potentially weeks or even months, offering unprecedented opportunities to study the dark zones in detail. Regardless of their origin, whether complex inorganic chemistry or potentially biological, these dark zones have profound implications for our understanding of Venus. They significantly affect the planet's energy balance, absorbing large amounts of solar radiation that would otherwise further heat the already scorching surface. Climate models suggest that without these UV absorbers, Venus's surface temperature could be up to 10 degrees Celsius, 18 degrees Fahrenheit, higher than the already extreme 462 degrees Celsius, 864 degrees Fahrenheit it currently experiences. Thus, these dark zones play a crucial role in the thermal regulation of the Venusian atmosphere. Furthermore, the chemistry associated with these absorbing regions likely contributes to Venus's broader geochemical cycles. If sulfur compounds are involved, as many scientists suspect, then these dark zones represent an important part of the planet's sulfur cycle, affecting how this element circulates between the surface and atmosphere. The non-uniform distribution of these zones also influences atmospheric circulation patterns. By absorbing UV radiation in specific locations, they create temperature gradients that can alter local wind patterns, potentially contributing to the circulation anomalies observed in the Venusian atmosphere. One of the most recent discoveries related to these dark zones came from observations made by the Hubble Space Telescope in 2022. These observations revealed that some of the absorbing regions appear to form spiral structures that extend for hundreds of kilometers. These spiral formations show internal rotation, like small vortices within the broader atmosphere. The behavior of the vortices is particularly intriguing because they seem to maintain their structural integrity for surprisingly long periods, resisting dispersion by the strong Venusian winds. This suggests there is some active mechanism that keeps these structures cohesive, whether a complex physicochemical process or, in the more speculative hypothesis, some kind of coordinated behavior if they are aggregations of microorganisms. As new observation and exploration technologies are developed, our understanding of these mysterious dark zones will continue to evolve. They remain one of the most intriguing phenomena not only on Venus but in the entire solar system, a reminder that even on our closest planetary neighbors, there are still fundamental enigmas awaiting resolution. These complex structures and vortices in Venusian clouds are even more fascinating when we consider one of the most extraordinary phenomena in our solar system, Venus's atmospheric superrotation. As we observe the dark zones and their intriguing movements, we are witnessing only a small part of a climate system that defies our fundamental understanding of planetary atmospheric dynamics. To understand how extraordinary this phenomenon is, we need to compare two numbers that seem almost irreconcilable. Venus completes one rotation around its own axis every 243 Earth days, rotating slowly and curiously in the opposite direction to most other planets. This makes a Venusian day longer than its year, since the planet takes only 225 Earth days to complete an orbit around the Sun. However, if we observe Venusian clouds, we see something completely different. The planet's upper atmosphere rotates at an impressive speed, completing one turn around the planet in just 4 Earth days. This means that Venus's clouds move approximately 60 times faster than the planet's surface below them. This extreme decoupling between surface rotation and atmosphere has no parallel on any other planet in the solar system. The winds that drive this superrotation reach speeds of approximately 360 kilometers, 224 miles, per hour in the upper layers of the atmosphere. To contextualize, this is significantly faster than Earth's most powerful hurricanes. These winds blow almost uniformly from east to west, creating a global flow that envelops the entire planet. What makes this phenomenon even more intriguing is that, according to basic laws of atmospheric physics, this shouldn't happen. Normally, friction between a planet's atmosphere and surface should cause the atmosphere to move over time at approximately the same speed as the surface. On Venus, something is injecting an enormous amount of energy into the atmosphere to maintain this superrotation against the forces of friction. One of the most persistent features of this superrotation are the Y-shaped structures that have been observed in Venus's clouds since the first detailed photographs of the planet in the 1970s. These Y formations extend for thousands of kilometers and, surprisingly, can persist for decades, despite atmospheric turbulence and extreme winds. The Japanese space agency's Akatsuki probe, which arrived at Venus in 2015 after a failed first attempt, captured detailed images of these Y structures. Most disconcerting is that these formations seem to maintain their structural integrity for much longer periods than would be expected in such a dynamic system. It's as if there were stable atmospheric rivers within the broader flow of superrotation. NASA scientists have developed sophisticated computer models to try to explain how this superrotation is maintained. One of the most accepted theories involves a mechanism known as the thermal tide pump. When the Sun heats Venus's day side, the air expands and rises. This rising air creates atmospheric waves that transport angular momentum, essentially rotational energy, to the upper layers of the atmosphere. Additionally, gravity waves, not to be confused with gravitational waves, these are waves that occur in a fluid whose restoring force is gravity, generated by airflow over mountains and other topographical features of Venus, also seem to play a crucial role. These waves transfer energy from the slow rotation of the surface to the fast-moving atmosphere, helping to maintain the superrotation. A particularly fascinating aspect of this system is that it is not uniform across the planet. Superrotation varies in intensity between the equator and poles, creating shear zones where different atmospheric layers move at different speeds. These shear zones, in turn, generate turbulence and secondary structures such as the Y formations mentioned earlier. Recent studies using data from the European Space Agency's Venus Express mission, which operated from 2005 to 2014, revealed another surprising aspect. Venus's superrotation is not constant over time. There is evidence that wind speeds in the upper layers can vary by up to 20% over periods of a few Earth years. This variability suggests that the Venusian atmosphere is even more complex than initially thought. Some scientists propose that there could be long-term atmospheric cycles on Venus, something analogous to our El Niño cycles or Arctic oscillations, but operating on much larger timescales. Perhaps most surprising is the discovery of variations that could be considered seasonal in Venusian clouds. This is extremely unexpected because Venus has an almost perfectly vertical rotation axis, only 3 degrees of inclination compared to Earth's 23 degrees. This small inclination means Venus shouldn't experience seasons in the conventional sense, since the amount of sunlight reaching any latitude remains practically constant throughout the Venusian year. However, long-term observations show cyclical changes in cloud patterns and concentrations of certain atmospheric gases that seem to follow a temporal pattern related to Venus's orbit around the Sun. These pseudo-seasons could be caused by subtle interactions between solar radiation, atmospheric dynamics, and possibly even gravitational influences from other planets. One of the most recently discovered aspects of the Venusian atmosphere are the so-called atmospheric rivers, currents of high water vapor density and other compounds that flow like discrete rivers within the broader atmospheric flow. These atmospheric rivers were detected by the Akatsuki probe and represent a new level of complexity in understanding Venusian atmospheric dynamics. These atmospheric rivers seem to play an important role in transporting chemical compounds between different regions of the atmosphere. They may explain how certain chemical substances remain concentrated in specific regions, rather than mixing uniformly throughout the atmosphere, as would be expected in such a turbulent system. The energy needed to maintain this entire dynamic system comes mainly from the Sun. Venus receives approximately twice as much solar radiation as Earth due to its greater proximity to the Sun. This energy is partially reflected by the highly reflective clouds. Venus has the highest albedo reflectivity of any planet in the solar system, but the portion that is absorbed fuels the powerful winds and extreme weather patterns. Venus's climate system is also characterized by surprising thermal stability between day and night, despite extremely long days. Venus's dense atmosphere, composed mainly of carbon dioxide and 93 times more massive than Earth's, acts as a gigantic heat reservoir. This efficiently distributes energy around the planet, resulting in a temperature difference of only a few degrees between the day side and night side, in stark contrast to Mercury or the Moon, where this difference can reach hundreds of degrees. This efficient heat transport is facilitated by superrotation. Rapid winds carry heat from the day side to the night side, preventing the sun-facing side from becoming much hotter than the dark side. This creates a planet with an almost uniform surface temperature of approximately 462 degrees Celsius, 864 degrees Fahrenheit, hot enough to melt lead. One of the most intriguing features of the Venusian climate is what scientists call the polar Hadley cell. On Earth, we have Hadley cells in equatorial regions, circulation patterns where hot air rises at the equator, moves toward the poles in the upper atmosphere, descends at middle latitudes, and returns to the equator near the surface. On Venus, similar cells extend from each pole to approximately 60 degrees latitude, creating immense and stable polar vortices. These polar vortices on Venus are massive atmospheric structures that can change shape dramatically, sometimes assuming dipole or even tripole configurations. The Venus Express probe observed the south polar vortex changing its configuration over days or weeks, demonstrating the dynamic nature of the Venusian climate system even in its most stable regions. Another fascinating aspect of atmospheric superrotation is how it affects the distribution of aerosols and particles in Venusian clouds. The strong zonal winds, which circle the planet longitudinally, tend to homogenize the distribution of particles along latitudinal bands. However, vertical and meridional north-south currents create complex distribution patterns, resulting in the characteristic bands and markings visible in ultraviolet images of Venus. The implications of Venus's atmospheric superrotation extend beyond understanding this specific planet. The study of this extreme phenomenon helps us test and refine our general atmospheric circulation models, which are fundamental for understanding not only other planets, but also Earth itself and its climate changes. Furthermore, as we discover more exoplanets, planets orbiting other stars, we find many worlds that likely have conditions more similar to Venus than to Earth. Understanding Venusian atmospheric dynamics can help us interpret the limited data we can obtain about these distant planets. Future missions to Venus, including NASA's recently approved Da Vinci Plus and Veritas, will provide new insights into atmospheric superrotation. These missions will use advanced sensing technologies to study the Venusian atmosphere in unprecedented detail, potentially answering many of the questions that persist about this extraordinary phenomenon. As we continue to study this extraordinary phenomenon, Venus's atmospheric superrotation remains one of the great mysteries of our solar system. A reminder that even our closest planetary neighbors still have much to teach us about the diversity and complexity of planetary climate systems. Our understanding of these complex Venusian climate systems didn't appear out of nowhere. It was patiently built over decades of space exploration. Since the early days of the space age, Venus has been a priority target for investigation, with each mission adding new pieces to the puzzle. To truly appreciate how far we've advanced in our knowledge about Venusian clouds, we need to look at the remarkable history of the missions that brought us here. The scientific journey toward Venus began seriously in the 1960s, when the space race between the United States and Soviet Union was at its height. The first probe to make a successful observation of Venus was NASA's Mariner 2, which flew by the planet in December 1962, becoming the first spacecraft to successfully visit another planet. Although it didn't capture images of the surface or clouds due to technological limitations of the time, its instruments confirmed Venus's scorching temperature and crushing atmospheric pressure. This first encounter revealed a planet very different from what scientists expected. Before the space age, some astronomers speculated that under Venus's clouds there might exist a wet tropical world, perhaps even habitable. Mariner 2 destroyed that notion, detecting surface temperatures of approximately 460 degrees Celsius, 860 degrees Fahrenheit. However, its instruments also made the first direct measurements of Venusian clouds, confirming their stratified nature and detecting their high-speed movements, the first glimpse of the superrotation we discussed earlier. After this initial mission, the Soviets took the lead in Venus exploration with their Venera program. The first successful mission of this program, Venera 4 in 1967, was the first to enter the Venusian atmosphere and transmit data directly from inside the clouds before being destroyed by pressure and heat. The following missions, Venera 5 and 6, also penetrated the atmosphere in 1969, providing more detailed measurements of the chemical composition of the clouds. The real breakthrough came with Venera 7 in 1970, which became the first probe to successfully land on the surface of another planet. Although it survived only 23 minutes in the infernal heat, its achievement marked a historic moment in planetary exploration. Subsequent Venera missions continued improving probe design to withstand the extreme conditions, culminating with Venera 9 and 10 in 1975, which sent the first images of the Venusian surface. Meanwhile, NASA was planning its own comprehensive attack on the planet. The Pioneer Venus mission, launched in 1978, consisted of 2 spacecraft, an orbiter and a multi-probe that split into 4 smaller probes to enter the atmosphere at different locations. This mission was specifically designed to study Venusian clouds in unprecedented detail. The Pioneer Venus orbiter operated for 14 years, far beyond its planned life expectancy, and revolutionized our understanding of Venus's clouds. Its instruments mapped the different cloud layers, measuring their composition, structure, and dynamics. It was this mission that definitively established that Venusian clouds are composed mainly of sulfuric acid droplets, not water as Earth's clouds are. The Pioneer Venus atmospheric probes made equally important discoveries. They detected 3 distinct cloud layers extending from approximately 48 to 70 kilometers, 30 to 43 miles above the surface. They also observed suspended particles of various sizes and compositions, including the mysterious ultraviolet absorbers mentioned earlier. One of the most significant discoveries of the Pioneer Venus mission was the precise identification of the atmospheric superrotation pattern. The instruments on board measured winds of up to 360 kilometers, 224 miles, per hour in the upper layers of the clouds, confirming that the atmosphere really circulated the planet in just 4 Earth days. After the success of the Pioneer and Venera missions, there was a hiatus in Venus-focused exploration. NASA turned its attention to Mars and more distant planets, while the collapse of the Soviet Union ended their Venera program. However, Venus wasn't completely forgotten. NASA's Galileo probe, on its way to Jupiter, made 2 Venus flybys in 1990 for gravitational assist maneuvers, taking advantage of the opportunity to collect more data about the planet's clouds. The renaissance of dedicated Venus exploration came in 2005 when the European Space Agency, ESA, launched the Venus Express mission. This probe, which operated until 2014, was specifically designed to study the Venusian atmosphere in detail. Using more advanced instruments than its predecessors, Venus Express provided unprecedented insights into the structure and dynamics of the clouds. One of the most significant contributions of Venus Express was the long-term study of variations in Venusian clouds. During its 8 years in orbit, the probe observed seasonal and cyclical changes in cloud patterns that had never been documented before. Its instruments also detected signs of recent volcanic activity affecting atmospheric composition, suggesting a connection between surface geology and cloud characteristics. Venus Express made surprising discoveries about Venus's polar vortices. Using infrared cameras, the probe captured detailed images of the south polar vortex, revealing a double structure that constantly changes shape but maintains an overall stability over time. These observations provided important clues about the mechanisms that drive global atmospheric circulation. Perhaps the most intriguing discovery of Venus Express was the detection of a tenuous ozone layer in the upper atmosphere. This discovery was unexpected, since ozone on Earth is mainly produced by the interaction of solar radiation with molecular oxygen, which is almost non-existent in the Venusian atmosphere. This suggested that unknown chemical processes could be occurring in the upper layers of the clouds. In 2010, Japan entered the Venus exploration scene with the Akatsuki probe, which means dawn in Japanese. The mission began with a setback when the spacecraft failed to enter orbit around Venus on its first attempt. In a remarkable demonstration of ingenuity, mission controllers managed to reposition the probe for another attempt 5 years later, in December 2015, which was successful. The story of Akatsuki is particularly inspiring as an example of scientific perseverance. After the initial failure, engineers discovered that the probe's main engine had been damaged. Instead of abandoning the mission, they developed an alternative plan using the spacecraft's attitude thrusters, designed only for small orientation adjustments to perform the orbital insertion maneuver. This bold plan worked, although it resulted in a more elliptical orbit than originally planned. Since then, Akatsuki has provided some of the most detailed images ever obtained of Venusian clouds. Its 5 camera instruments, each sensitive to different wavelengths, allow scientists to observe different layers of the atmosphere simultaneously. This revealed connections between phenomena occurring at different altitudes that had never been observed before. One of Akatsuki's most significant discoveries was the identification of a giant stationary atmospheric wave in Venus's upper clouds. This structure, which extends for 4,000 kilometers, 2,485 miles, from end to end, remains fixed over a mountain chain on the surface, even as the clouds around it are carried by superrotation winds. This observation provided direct evidence of how surface topography can influence the atmosphere even at altitudes of more than 50 kilometers, 31 miles, helping to explain some of the regional variations in cloud patterns. The compilation of data from all these missions over 6 decades has created an unprecedented historical record that allows scientists to identify long-term trends in Venusian clouds. For example, comparative analyses of observations from Mariner 10, 1974, Pioneer Venus, 1978 to 1992, Galileo, 1990, Venus Express, 2005 to 2014, and Akatsuki, 2015 to present, revealed long-term climate oscillations that would not be detectable by any individual mission. These long-term trends include variations in sulfur dioxide concentrations in the upper clouds, changes in the overall opacity of the clouds, and subtle alterations in superrotation rates. Some of these variations seem to follow cycles of approximately 10 to 15 Earth years, although the cause of these cycles remains unknown. A fascinating aspect of this exploration history is how each mission built upon knowledge acquired by previous ones. For example, Mariner 2's observations about Venus's high temperatures led to the design of Venera probes, specifically built to withstand extreme conditions. The Venera discoveries about cloud composition directly influenced the instruments chosen for the Pioneer Venus mission. The long-term data from Pioneer Venus in turn helped formulate the scientific questions addressed by Venus Express. This evolution continued with Akatsuki, whose instruments were specifically designed to investigate phenomena observed by Venus Express, such as variations in ultraviolet absorbers and atmospheric circulation patterns. Each mission not only answered questions raised by previous ones, but also generated new questions for future explorations. The history of Venus missions also demonstrates the international nature of modern planetary exploration. Although beginning as a competition between superpowers during the Cold War, Venus exploration has evolved into a collaborative effort involving space agencies from the United States, Russia, Europe, Japan, and more recently India, whose Shukrayan orbiter is in development. This international collaboration continues to expand our knowledge about Venusian clouds and sets the stage for a new era of exploration that may finally answer some of the most persistent questions about our enigmatic planetary neighbor. This international collaboration in Venus exploration has brought us one of the most surprising discoveries about our neighboring planet. While Venus's surface is an absolutely hostile environment to life as we know it, there is a region in the planet's clouds that, paradoxically, could be one of the most habitable environments in the solar system beyond Earth. This possibility, although still speculative, has gained increasing scientific credibility as we accumulate more data about the middle layers of the Venusian atmosphere. The idea of habitability in Venus's clouds may seem absurd at first glance, especially considering everything we've already discussed about its acidic composition and extreme conditions. However, NASA scientists have identified a specific band in the middle cloud layers, between 50 and 60 kilometers, 31 and 37 miles above the surface, where conditions are surprisingly mild. At this altitude, temperature varies between 0 and 50 degrees Celsius, 32 and 122 degrees Fahrenheit, and atmospheric pressure is similar to what we experience on Earth's surface at sea level, approximately 1 atmosphere. This temperate zone represents a kind of atmospheric Goldilocks, neither too hot like the infernal surface below, nor too cold like the upper layers of the atmosphere. It's as if Venus had a thin habitable layer floating in its sky, while its surface remains completely inhospitable. Astrobiologist David Grinspoon, who has studied Venus for decades, often describes this region as the most Earth-like environment in the solar system. A surprising statement considering we're talking about a planet generally seen as the ultimate example of an inhospitable world. However, when we consider only the parameters of temperature and pressure, the comparison is valid. Of course, there's a big problem we can't ignore: sulfuric acid. Venus's clouds are composed mainly of concentrated droplets of this extremely corrosive acid, creating a chemical environment that would quickly destroy any form of terrestrial life directly exposed to it. However, scientists propose some ways hypothetical organisms could potentially survive in these conditions. One of the most interesting theories, proposed by NASA scientist Sanjay Limaye and his colleagues, suggests that water droplets could temporarily exist within the acidic clouds, providing isolated microenvironments where life could potentially exist. These water droplets would function as small protected habitats within the broader acidic environment. This idea isn't as far-fetched as it initially seems. On Earth, we know many examples of microorganisms that live in extremely acidic environments, such as volcanic hot springs and acidic mine drainage. These acidophiles have developed specialized cell membranes and biochemical mechanisms that allow them not only to survive, but thrive at pH as low as 0, more acidic than car batteries. A particularly relevant example is the bacterium Acidithiobacillus, which lives in environments with pH between 1 and 2 and obtains energy by oxidizing sulfur compounds, exactly the kind of chemistry we would expect to find in Venusian clouds. If microorganisms on Earth can adapt to such extreme conditions, it's not completely implausible that life could have evolved to handle the acidic environment of Venus's clouds. Moreover, detailed spectroscopic analyses have revealed the presence of complex organic compounds in these middle layers of Venusian clouds. In 2016, the Venus Express probe detected structures that, on Earth, are typically associated with biological processes. These include organic molecules with spectral signatures similar to certain pigments used by terrestrial microorganisms to absorb harmful ultraviolet radiation. It's important to note that the presence of these organic compounds doesn't prove that life exists on Venus. They could be formed by non-biological chemical processes that we don't yet fully understand. However, their detection adds another intriguing piece to the puzzle. A factor often overlooked in discussions about planetary habitability is environmental stability. Environments that change drastically over short periods are generally more challenging for life than those that remain relatively constant. In this aspect, the middle layers of Venusian clouds offer a surprising advantage. Despite the superrotation winds that circle the planet at hundreds of kilometers per hour, the middle cloud layers experience less vertical turbulence than other atmospheric regions. This creates relatively stable zones that could allow the development of microbial ecosystems adapted to them. Additionally, this region of the Venusian atmosphere offers something essential for life as we know it, a usable energy gradient. The condensation and evaporation cycles in these layers create a dynamic system that could provide energy for potential life forms. On Earth, many microorganisms obtain energy through redox reactions, chemical reactions involving electron transfer between molecules. In Venus's clouds, similar chemical gradients exist between compounds in different oxidation states, particularly involving sulfur and iron. Hypothetical Venusian microorganisms could potentially exploit these differences to obtain energy, just as certain terrestrial bacteria use sulfur gradients in extreme environments like underwater hot springs. To test the plausibility of this hypothesis, scientists have conducted laboratory experiments simulating the conditions of the middle layers of the Venusian atmosphere. A particularly interesting study conducted by NASA researchers in 2021 demonstrated that certain terrestrial extremophiles can survive in conditions similar to those found in these temperate zones of Venusian clouds, at least for limited periods. In these experiments, scientists exposed various species of microorganisms to gas mixtures similar to the Venusian atmospheric composition, including high concentrations of carbon dioxide and traces of sulfuric acid. Surprisingly, some extremophilic bacteria and archaea demonstrated the ability to survive and even metabolize in these conditions for several weeks. Of course, there are significant differences between surviving for a few weeks in a simulated environment and evolving to thrive in real conditions for millions of years. However, these experiments demonstrate that carbon-based biochemistry as we know it on Earth is not fundamentally incompatible with the conditions in the middle layers of Venusian clouds. A question frequently raised is, if there is potential for life in Venus's clouds, how would it have originated? Life on Earth likely began in aquatic environments on the surface or near hydrothermal vents on the ocean floor. But how could life have arisen directly in an atmosphere? One hypothesis is that Venus wasn't always the infernal world we know today. Geological evidence and climate models suggest the planet may have had oceans of liquid water for up to 2 billion years in its remote past. During this period, Venus could have been potentially habitable on its surface, perhaps even developing primitive microbial life. When the runaway greenhouse effect transformed the planet, raising surface temperatures beyond the boiling point of water, any organisms that had developed the ability to survive as atmospheric aerosols, perhaps something similar to bacteria that are transported in Earth's atmosphere today, could have found refuge in the higher, cooler layers of the atmosphere. This idea, although speculative, is not without precedent on Earth. We know that our own atmosphere contains a surprising diversity of microorganisms living as aerosols, the so-called aerial biosphere. These organisms can remain viable in the atmosphere for weeks or even months, being transported thousands of kilometers. A particularly interesting feature of the middle layers of Venusian clouds is the presence of ultraviolet radiation at levels that would be harmful to many forms of terrestrial life. However, this doesn't necessarily exclude the possibility of life. On Earth, many microorganisms have developed protection mechanisms against UV radiation, including specialized pigments, DNA repair mechanisms, and the formation of protective biofilms. Interestingly, the mysterious UV absorbers we mentioned earlier, the particles in Venusian clouds that strongly absorb ultraviolet radiation, share some spectroscopic properties with certain terrestrial biological pigments. Scientists like Sanjay Limay speculate that at least some of these absorbers could potentially be of biological origin, perhaps serving as UV protection for hypothetical Venusian microorganisms, just as pigments like melanin protect terrestrial organisms. The hypothesis of habitability in Venusian clouds gained new attention after the detection of phosphine we discussed earlier. If confirmed, the presence of this potential biomarker precisely in the same atmospheric region that had already been identified as potentially habitable based on physical parameters would be a remarkable coincidence. It's important to emphasize that despite these intriguing observations, we still don't have conclusive evidence of life on Venus. What we have is a growing set of observations suggesting that the middle layers of Venusian clouds are much more hospitable to life than previously thought, and some chemical and physical features that are difficult to explain through known abiotic processes. To really determine if there is life in Venus's clouds, we will need dedicated missions that can collect samples directly from these middle layers and analyze them with sophisticated instruments. Fortunately, several missions are being planned that could address this question, including atmospheric balloons and specialized probes designed to float precisely in this habitable zone of Venusian clouds. If we eventually discover that life really exists in Venus's clouds, the implications would be profound. It would not only drastically expand our understanding of the limits of life, but also suggest that life may be much more common in the universe than we currently estimate. If two planets in a single solar system developed life independently, or even if life found ways to persist in an environment as extreme as Venusian clouds, then the possibilities for life in other stellar systems would become much broader. This possibility of life in Venus's clouds makes us question how a planet that may harbor potentially habitable conditions in its atmosphere developed such an extremely hostile surface. To understand this paradox, we need to look at Venus's past and the dramatic history of its atmospheric evolution. The evidence that NASA and other space agencies have gathered suggests a surprising narrative. Venus may not always have been the infernal world we know today. Various geological and atmospheric studies indicate that primitive Venus probably had much in common with primitive Earth. Computer simulations of planetary formation suggest that, like Earth, Venus should have received substantial amounts of water during its formation. In fact, given its mass and composition similar to Earth's, scientists believe that Venus probably possessed oceans of liquid water on its surface for a significant period. perhaps up to 2 billion years of its early history. The evidence for this wet past comes from several sources, but one of the most convincing is in Venus's current clouds themselves. Detailed spectroscopic analyses of the Venusian atmosphere reveal isotopic signatures that tell a story of massive water loss. Specifically, the ratio of deuterium, a heavy isotope of hydrogen, to regular hydrogen in Venus's atmosphere is approximately 150 times higher than on Earth. This elevated deuterium ratio is a chemical fingerprint that clearly indicates Venus once had much more water than it has today. This occurs because when water breaks down in the upper atmosphere and hydrogen escapes into space, a process that occurs on both planets, the lighter regular hydrogen escapes more easily than the heavier deuterium. Over time, this leads to a relative enrichment of deuterium in the remaining water. The amount of enrichment observed on Venus suggests the planet may have lost an entire ocean of water, perhaps a volume comparable to Earth's oceans. But if Venus once had oceans like Earth, what happened to them? The answer lies in a catastrophic climate process that scientists call the runaway greenhouse effect. Atmospheric models developed by NASA show how Venus's slightly greater proximity to the Sun, receiving approximately twice as much solar radiation as Earth, created the conditions for a downward climate spiral. The process likely began gradually, as the young Sun slowly heated up over billions of years, a normal stellar evolution. Venus's surface temperature was gradually increasing. Eventually, it reached a critical point where the oceans began to evaporate more rapidly, increasing water vapor in the atmosphere. Since water vapor is a powerful greenhouse gas, this further raised the temperature, causing more evaporation, in a classic example of positive feedback. As temperatures continued to rise, another crucial process came into play. Carbon dioxide, which on Earth is largely trapped in carbonate rocks, began to be released from the Venusian crust. On Earth, we have a carbon cycle where atmospheric CO2 is absorbed by the oceans and eventually incorporated into sedimentary rocks. On Venus, the increasing temperature began to reverse this process, releasing enormous additional quantities of CO2 into the atmosphere. This double blow, loss of oceans that could absorb CO2 and release of additional CO2 from rocks, dramatically accelerated the greenhouse effect. Surface temperatures rose beyond the boiling point of water, ensuring that no liquid ocean could reform. Eventually, Venus's atmosphere transformed into the thick carbon dioxide cover we see today, with a surface pressure 92 times greater than Earth's. The dense clouds of sulfuric acid that now envelop Venus are the final stage of this atmospheric transformation. Evidence suggests they formed as a result of complex reactions involving sulfur dioxide released into the atmosphere by intense volcanic activity. On an already overheated planet with a CO2-rich atmosphere, these volcanic emissions reacted to form the sulfuric acid that characterizes current Venusian clouds. A particularly intriguing aspect of this story is what it tells us about the habitable zone around stars. Traditionally, astronomers defined the habitable zone as the region around a star where liquid water could exist on a planet's surface. According to this conventional definition, Venus is slightly inside the inner limit of our Sun's habitable zone. That is, it could theoretically have maintained liquid water on its surface. The fact that Venus underwent a runaway greenhouse effect, despite being only marginally inside the inner limit of the habitable zone, suggests that this zone may be narrower than previously thought. Alternatively, it suggests that other factors beyond simple distance from the star, such as initial atmospheric composition, planetary rotation, or the presence of a strong magnetic field, may be crucial for maintaining habitable conditions in the long term. One of the most powerful tools for studying this atmospheric evolution are the isotopic signatures present in the current atmosphere. Beyond the deuterium/hydrogen ratio mentioned earlier, NASA scientists have studied ratios of isotopes of other elements such as neon, argon, and xenon. Each of these isotopic clocks provides information about different aspects of Venus's atmospheric history. For example, the ratios of noble gas isotopes like argon-36 and argon-38 suggest that Venus suffered a massive atmospheric loss event in its remote past. This is consistent with the theory that Venus lost not only its water, but also significant parts of its original atmosphere. Understanding the details of this atmospheric transformation has implications that go far beyond our curiosity about Venus's past. NASA and other climate scientists have used Venus as an extreme case study to refine Earth climate models and better understand the risks of tipping points on our own planet. Although Earth is not at immediate risk of a complete Venusian greenhouse effect, we are much farther from the Sun. Certain aspects of the climate feedback observed on Venus have worrying parallels with terrestrial processes. For example, just as Venus's warming released additional CO2 from rocks, global warming on Earth has the potential to release additional greenhouse gases from natural reservoirs such as Arctic permafrost or methane hydrates on the ocean floor. These sources of positive feedback are one of the biggest concerns in the context of terrestrial climate change. Additionally, the study of Venusian clouds has helped scientists improve models of how aerosols and particles in the atmosphere affect a planet's energy balance. On Earth, this is an area of significant uncertainty in climate models. How exactly different types of clouds and atmospheric particles affect warming or cooling. Venus's clouds, being an extreme case, provide a useful point of comparison. A particularly intriguing question is whether Venus could someday return to a more habitable state. Some scientists have proposed terraforming concepts, deliberate planetary transformation that could theoretically, over thousands of years, convert Venus into a world more similar to Earth. These proposals generally involve somehow removing excess CO2 from the atmosphere or blocking part of the solar radiation to allow the planet to cool. Although such proposals remain firmly in the realm of science fiction with our current technology, the study of Venusian atmospheric evolution helps us understand which aspects of a planetary climate are potentially reversible and which represent permanent changes. For example, even if we could somehow cool Venus, the water lost to space could never be naturally recovered. A fascinating aspect of Venus's atmospheric history is how it may have affected any life that possibly arose there. If Venus really had oceans and moderate surface conditions for hundreds of millions or billions of years, there is a possibility that microbial life could have developed during this habitable period. As the greenhouse effect began to transform the planet, any hypothetical life would have faced intense evolutionary pressures. Most would likely have been extinct as the oceans evaporated and surface temperatures became incompatible with water-based biochemistry. However, some scientists speculate that organisms could have gradually adapted to inhabit the higher, cooler layers of the atmosphere, eventually evolving into forms that could survive in current conditions of Venusian clouds. This scenario offers a possible explanation for the question of how life could exist in an atmospheric environment. It may not have originated there, but migrated there as a last refuge from a transforming planet. This would also explain how organisms could have developed the extreme adaptations necessary to survive in the acidic conditions of current clouds. They would have had millions of years to gradually adapt as the planet slowly changed. NASA plans to further investigate this atmospheric evolution with future missions to Venus. The Da Vinci Plus mission. Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging Plus, scheduled for launch in the coming years, will make precise measurements of noble gases and their isotopes in the Venusian atmosphere. This data will allow much more detailed reconstructions of the planet's atmospheric history. Another planned mission, VERITAS, Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy, will use advanced radar to map Venus's surface in unprecedented detail. These observations could reveal geological evidence of ancient oceans, such as fossilized coastlines or rock formations that would only form in the presence of liquid water. Together, these missions promise to transform our understanding of Venus's history and provide valuable insights into how potentially habitable planets can lose their favorable conditions for life. Venus's atmospheric history serves as a powerful reminder of the delicate interconnection between a planetary surface, its atmosphere, and the conditions that allow the existence of liquid water, the essential ingredient for life as we know it. The transformation of Venus from a potentially Earth-like world to the planetary hell we observe today is a story of climate change in its most extreme form. By studying this transformation, we gain a deeper appreciation of the luck we've had on our own planet, where distance from the Sun, atmospheric composition, and other factors have combined to maintain habitable conditions for billions of years. We also gain a warning about how dramatically planetary systems can change when certain limits are crossed. To study this dramatic atmospheric transformation of Venus and verify all theories about its history and potential habitability, scientists needed to develop extremely innovative technologies. After all, exploring Venus's clouds is not a simple task. We're talking about one of the most hostile and corrosive environments in the solar system. Common technology simply doesn't work in these conditions, which led NASA and other space agencies to develop truly revolutionary solutions to enable exploration of this challenging environment. The first major obstacle to overcome is the extremely corrosive nature of Venusian clouds. The concentrated sulfuric acid droplets that make up these clouds are capable of rapidly corroding most conventional materials. This became evident from the first Soviet Venera probes, which, even protected by thermal shields and special coatings, managed to survive only for very short periods. The most durable functioned for just 2 hours on the surface. To face this challenge, NASA engineers developed a new generation of acid-resistant materials that far surpass the protections used in previous missions. Among the most promising innovations are zirconium silicate-based coatings, which have demonstrated exceptional resistance in tests simulating Venusian atmospheric conditions. These materials can withstand direct exposure to concentrated sulfuric acid for weeks or even months without significant degradation. Another innovative approach involves the use of advanced fluorinated polymers, similar to Teflon but with much superior chemical resistance. Scientists at NASA's Jet Propulsion Laboratory have developed compounds that maintain their structural integrity even after prolonged exposure to concentrated sulfuric acid at temperatures up to 200 degrees Celsius, 392 degrees Fahrenheit. These materials are particularly important for protecting sensitive electronic components inside the probes. Beyond materials, a second fundamental challenge is the very means of exploration. Unlike Mars, where surface rovers are the main exploration tool, Venus requires a completely different approach due to its extremely hostile surface. The most promising solution has been the development of aerial platforms, specifically aerostats and robotic balloons capable of floating in the middle layers of the Venusian atmosphere. NASA engineers have designed a new generation of robotic balloons that can maintain controlled altitude in atmospheric layers of interest, typically between 50 and 60 kilometers, 31 and 37 miles above the surface, where temperatures and pressures are more moderate. These balloons use multi-layer envelopes made of special polymers that resist both acid and intense ultraviolet radiation. The most advanced concept is what scientists call aerobots, robotic balloons equipped with control systems that allow them to rise or descend in the Venusian atmosphere to sample different cloud layers. These devices can change their buoyancy by heating or cooling an internal balloon gas, allowing them to explore the atmosphere vertically without needing conventional propellers that would consume too much energy. In 2022, NASA successfully tested a prototype altitude control system for Venusian balloons in Earth's atmosphere. The system managed to maintain a target altitude with precision of plus or minus 50 meters, 164 feet, even in variable wind conditions. A crucial capability for any mission that intends to study specific layers of Venusian clouds. Even with suitable platforms, another challenge is how to actually analyze the composition of the clouds. For this, extremely advanced spectroscopy technologies have been developed. Miniaturized mass spectrometers capable of detecting compounds in concentrations of parts per billion represent a giant leap compared to instruments used in previous missions to Venus. These new spectrometers use electromagnetic fields to separate molecules based on their mass and charge, allowing precise identification of complex organic compounds, potential biomarkers, and other chemical components of interest. Most impressive is that these instruments have been miniaturized to the point of weighing less than 2 kilograms, 4.4 pounds, compared to previous instruments that often weighed 10 times more. Complementing the mass spectrometers, new generations of infrared and ultraviolet spectrometers allow non-destructive analyses of cloud composition. Using tunable laser technologies, these instruments can identify specific compounds based on how they absorb different wavelengths of light. The precision is so high that scientists can distinguish between different isotopes of the same element, a crucial capability for understanding chemical and potentially biological processes. One of the biggest challenges for any mission to Venus is energy. The dense clouds block much of the available sunlight, reducing the efficiency of conventional solar panels. At the same time, extreme conditions make other energy sources problematic. To overcome this, engineers have developed solar cells specially optimized for the light spectrum filtered by Venusian clouds. These new generation solar cells use semiconductor materials that maximize absorption in the wavelengths that most easily penetrate Venus's clouds. Tests in chambers that simulate Venusian illumination show that these panels can generate up to 40% more energy than conventional solar cells under the same conditions. Additionally, they are designed with coatings that resist acid attack, ensuring long-term operation. For missions that need to explore deeper layers of the atmosphere, where sunlight is even more limited, small radioisotope thermoelectric generators, RTGs, have been adapted for Venusian conditions. These devices generate electricity from heat produced by the natural radioactive decay of elements such as plutonium-238, functioning continuously for decades without needing sunlight. A particularly exciting innovation in the field of Venusian exploration is the development of artificial intelligence algorithms specifically designed to detect anomalous patterns in the clouds. These AI systems can process enormous amounts of imaging and spectroscopy data, identifying features that might go unnoticed by human analysis. In tests using data from the Venus Express mission and the Japanese Akatsuki probe, these algorithms managed to identify previously unknown circulation patterns in the clouds and subtle variations in chemical composition that suggest active processes occurring in specific regions of the atmosphere. Particularly interesting was the ability of these systems to identify correlations between different phenomena, such as the relationship between specific cloud formations and elevated concentrations of certain chemical compounds. The true revolution, however, is in the miniaturization of sensors capable of functioning in extreme conditions. Sensors for temperature, pressure, chemical composition, and radiation have been reduced to sizes unimaginable just a decade ago, allowing even small probes to carry complete suites of scientific instruments. A notable example is the development of silicon carbide, SiC-based sensors, a semiconductor material that maintains its electrical properties even at temperatures exceeding 400 degrees Celsius, 752 degrees Fahrenheit. These sensors can operate in virtually any region of the Venusian atmosphere without needing active cooling, greatly simplifying probe design. Another crucial innovation is acid-resistant microelectromechanical systems, MEMS, which integrate sensors, actuators, and electronics on fingernail-sized silicon chips. These devices can measure acceleration, rotation, magnetic fields, and various atmospheric properties, all while consuming minimal amounts of energy and resisting the corrosive environment. Advances in communication technologies have also been fundamental in enabling more ambitious missions to Venus. High-efficiency radio transmitters, capable of sending data at much higher rates than previous missions, allow even relatively small probes to transmit large volumes of scientific information back to Earth. A particularly innovative concept is the use of a network of small balloons or disposable probes that can work together as a distributed system. Each unit carries a limited set of sensors, but collectively they can map spatial and temporal variations in Venusian clouds with unprecedented detail. These systems use inter-unit communication to coordinate observations and relay data back to Earth through an orbiter. What makes these technologies even more impressive is that many of them have applications that go far beyond space exploration. The acid-resistant materials developed for Venus have already found use in industrial chemical facilities on Earth. High-temperature sensors are being adapted for monitoring volcanoes and geothermal plants. And the AI algorithms developed to analyze Venusian atmospheric data are being applied to improve Earth climate models. NASA is also exploring the concept of long-duration atmospheric probes that could remain operational in Venusian clouds for years, not just days or weeks like previous missions. These Venusian weather stations would float in the habitable layers of the clouds, continuously collecting data on temperature, pressure, wind speed, chemical composition, and radiation. The most ambitious of the concepts currently in development is a probe that could not only measure cloud composition, but actively collect aerosol samples and subject them to biological analyses, equipped with instruments similar to those used to detect microbial life in extreme environments on Earth. This probe could potentially provide direct evidence of any biological activity in Venus's clouds. All these technological innovations are converging to make possible a new era of Venusian exploration that could finally answer some of the most fundamental questions about our neighboring planet. How did its atmosphere evolve over time? Are there active chemical or biological processes in its clouds? What can we learn from Venus about the climate evolution of planets in general? The lessons learned in developing these technologies are also informing plans for exploration of other worlds with extreme environments, such as the icy moons of Jupiter and Saturn, or even the clouds of other giant planets. The innovative solutions created for the unique challenges of Venus are expanding our technological repertoire for solar system exploration as a whole, showing that even the most hostile environments can be studied with the right tools. With all these revolutionary technologies being developed to explore Venus, scientists are particularly interested in investigating a fascinating atmospheric phenomenon that doesn't exist anywhere else in the solar system: the sulfuric acid-based hydrological cycle. While Earth has its familiar water cycle, with evaporation from oceans, cloud formation, and precipitation as rain or snow, Venus possesses an extremely exotic version of this fundamental process, using one of the most corrosive acids we know as its working fluid, T. This acidic hydrological cycle is completely different from anything we experience on Earth. In the Venusian atmosphere, sulfuric acid evaporates from the hotter lower layers of the atmosphere, rises to higher, cooler regions where it condenses into droplets, forms clouds, and eventually rains. But with a big difference: this acid rain never reaches the planet's surface. Infrared images captured by the Venus Express probe revealed what scientists call rain curtains of sulfuric acid extending for kilometers below the main cloud base. These precipitation curtains are visible as dark bands in infrared images, showing where larger acid droplets are falling through the atmosphere. The most extraordinary aspect is that, due to the extremely high temperatures in the lower layers of the Venusian atmosphere, these acid drops completely evaporate before reaching the surface. The result is a cycle perpetually confined to the atmosphere, a closed system where sulfuric acid continuously circulates through different atmospheric layers without ever accumulating on the surface. NASA scientists describe this as an incomplete hydrological cycle compared to Earth's, where water completes the circuit by returning to the surface. The increasing temperatures as acid rain falls create an effective boundary below which no liquid precipitation can exist. Data collected by atmospheric probes indicate that this boundary is located approximately 35 kilometers, 22 miles, above the Venusian surface, where the temperature reaches about 200 degrees Celsius, 392 degrees Fahrenheit. Hot enough to rapidly evaporate any sulfuric acid droplet. A particularly intriguing discovery came from penetrating radar analyses, which showed that this acid cycle doesn't just transport sulfuric acid itself, but also carries various minerals and chemical compounds between different layers of the atmosphere. It's as if Venus had invisible atmospheric rivers that transport elements like iron, chlorine, and sulfur through its clouds. This vertical transport creates chemical concentration gradients, essentially differences in chemical composition between different altitudes, that function as potential sources of chemical energy. On Earth, many microorganisms obtain energy by exploiting similar chemical gradients in extreme environments like hydrothermal vents. Some scientists speculate that if life exists in Venus's clouds, it could potentially utilize these gradients in a similar way. The sulfuric acid cycle on Venus is not uniform across the planet. NASA has identified significant regional variations, with some areas exhibiting greater condensation and evaporation activity than others. These differences create what we might call microclimates within Venusian clouds, regions with distinct characteristics in terms of droplet size, acid concentration, and precipitation rates. Data from the Akatsuki probe shows that these regional variations often correspond to topographical features on the surface below. For example, regions above large mountain elevations such as the Aphrodite Highlands tend to show more intense vertical circulation patterns, suggesting that, even with the enormous separation between the surface and clouds, Venusian topography still influences its acidic hydrological cycle. A fascinating aspect of this system is the role of volcanic dust as condensation nuclei for sulfuric acid droplets. Measurements made by atmospheric probes have detected microscopic particles of volcanic minerals floating in the middle layers of the Venusian atmosphere. These particles serve as surfaces on which sulfuric acid vapor can condense, very similar to how dust and salt function as condensation nuclei for water droplets in Earth's atmosphere. This connection between volcanism and cloud formation creates a direct link between Venus's geology and its atmospheric processes. When a Venusian volcano erupts, it not only releases gases like sulfur dioxide, which eventually contributes to the formation of more sulfuric acid, but also ejects fine particles that can alter cloud formation patterns for months or even years. Evidence of recent volcanic activity on Venus, detected by Venus Express as temporary peaks in sulfur dioxide concentrations in the upper layers of the atmosphere, suggests that this process continues to be active today. Each eruption potentially alters the balance of the acidic hydrological cycle, introducing new materials and causing fluctuations in cloud density and composition. The dynamics of this acidic hydrological cycle directly influence the opacity and reflectivity of Venusian clouds, thus controlling the planet's energy balance. Venus's clouds reflect approximately 75% of the sunlight that reaches the planet, an extremely high value that makes Venus the brightest object in Earth's night sky after the Moon. This high reflectivity, or albedo, is a crucial property for the Venusian climate. If the clouds were less reflective, allowing more solar energy to reach the surface, the already extreme surface temperatures could be even higher. Climate simulations suggest that without its reflective clouds, Venus's surface temperature could be approximately 50 to 100 degrees Celsius, 90 to 180 degrees Fahrenheit higher than the already scorching 462 degrees Celsius, 864 degrees Fahrenheit it currently experiences. The acidic hydrological cycle also creates a curious heat conservation effect. During the long Venusian day, which lasts approximately 117 Earth days, sulfuric acid droplets in the upper layers of the clouds absorb some of the infrared radiation emitted by the hot surface, contributing to the planet's intense greenhouse effect. When these droplets descend and evaporate, they release this heat in the middle layers of the atmosphere, helping maintain thermal stability between Venusian day and night. One of the most interesting properties of sulfuric acid in Venusian clouds is its ability to absorb water. Sulfuric acid is extremely hygroscopic, meaning it attracts and retains water molecules with great efficiency. On Earth, we use this property in industrial desiccants. On Venus, this characteristic causes any trace of water vapor in the atmosphere to be quickly absorbed by acid droplets in the clouds. This efficient water capture by sulfuric acid helps explain why the Venusian atmosphere is so extraordinarily dry, containing only about 20 parts per million of water vapor, compared with several percentages in Earth's atmosphere. Essentially, the sulfuric acid clouds function as water traps that keep the atmosphere dehydrated. Scientists have discovered that these acid droplets containing water form a complex mixture whose exact composition varies with altitude. In the lower layers of the clouds, where temperatures are higher, the solution contains approximately 85% sulfuric acid and 15% water. In the cooler upper layers, the water concentration can reach 25%. These variations in composition directly affect physical properties such as freezing point and viscosity of the droplets. In Venus's polar regions, where temperatures are slightly lower, some droplets in the upper clouds may even form crystals, not of pure ice as on Earth, but of sulfuric acid hydrate, a crystalline form containing both acid and water. Detailed spectral studies of Venusian clouds conducted by the Venus Express probe revealed another fascinating aspect of this acidic hydrological cycle. It seems to involve not just sulfuric acid but also other sulfur compounds in different oxidation states. These include sulfur dioxide, elemental sulfur, and possibly even sulfurous acid, creating a complex biogeochemical sulfur cycle that scientists are only beginning to understand. The interaction between these different sulfur compounds creates a dynamic chemical system where redox reactions, reactions that involve electron transfer between molecules, occur continuously. On Earth, such redox cycles often provide energy for microbial ecosystems, particularly in extreme environments like hydrothermal vents and volcanic acid lakes. The implications of Venus's acidic hydrological cycle extend beyond understanding this specific planet. Astronomers are increasingly detecting exoplanets, planets around other stars, that likely have surface temperatures similar to Venus. Understanding how the sulfuric acid cycle works on Venus can help us predict and interpret observations of these distant worlds. For example, observations from the Hubble and James Webb Space Telescopes are beginning to collect data about the atmospheres of some exoplanets. The presence of certain sulfur compounds in these atmospheres could indicate processes similar to what we see on Venus, potentially including hydrological cycles based on compounds different from water. Future missions to Venus, such as NASA's Da Vinci Plus and Veritas, will provide much more detailed measurements of this acidic hydrological cycle. The Da Vinci Plus probe, in particular, will descend through Venusian clouds, collecting real-time data on the composition, size, and concentration of acid droplets at different altitudes. These measurements will allow scientists to build much more precise models of how the cycle works and how it has evolved over Venus's geological time. There are also plans for missions that could float within the clouds themselves for extended periods. An atmospheric balloon could directly track the cycle of evaporation and condensation of sulfuric acid, perhaps even capturing droplets for detailed analysis of their composition. Fully understanding this unique hydrological cycle is not just a matter of scientific curiosity. It also has practical implications for our understanding of atmospheric processes and chemical cycles in general. The lessons learned studying this extreme system can inform our knowledge about biogeochemical cycles on Earth and help refine our models of how planetary atmospheres evolve and maintain themselves over billions of years. Venus's acidic hydrological cycle remains one of the most extraordinary and alien phenomena ever observed in our solar system. A reminder that even among neighboring planets, the fundamental processes that govern their climates can be dramatically different. To study this acidic hydrological cycle in detail and the other mysteries of Venusian clouds, NASA and other space agencies are planning a new generation of revolutionary missions that go far beyond anything we've ever sent to this enigmatic planet. After decades of focus on Mars and other destinations, Venus is finally receiving the attention it deserves, with ambitious missions specifically designed to answer the most intriguing questions about its mysterious clouds. In June 2021, NASA announced the approval of 2 new major missions as part of its Discovery program, Da Vinci Plus and Veritas. These missions, with launch planned for the end of this decade, represent the most significant return of the American Space Agency to Venus since Pioneer Venus in the 1970s. The Da Vinci Plus mission, acronym for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging Plus, is particularly revolutionary for the study of Venusian clouds. It consists of an orbiter and an atmospheric probe that will literally plunge through the cloud layers, collecting precise data about their composition during its approximately 1-hour descent to the surface. What makes Da Vinci Plus so innovative is its set of specialized instruments. The probe will carry a state-of-the-art mass spectrometer capable of identifying chemical compounds in concentrations of parts per billion. This instrument will be able to analyze with unprecedented precision the exact composition of sulfuric acid droplets, look for traces of phosphine and other potential biomarkers, and measure isotopic ratios of key elements that can reveal the history of the Venusian atmosphere. Additionally, Da Vinci Plus will be equipped with high-resolution cameras that will capture images of the clouds during descent, potentially revealing their structures in never-before-seen detail. One of these cameras is specifically designed to work in the ultraviolet range, allowing direct imaging of the mysterious UV absorbers we discussed earlier. The orbiter component of the mission will provide a broader context, mapping variations in the clouds on a global scale and monitoring them over time. This aspect is crucial since many of the most intriguing phenomena in Venusian clouds, such as the UV-absorbing dark zones, constantly change, requiring continuous observation to be fully understood. While Da Vinci Plus primarily focuses on the atmosphere, the Veritas mission, Venus emissivity, radioscience, INSAR, topography, and spectroscopy will complement these efforts with a focus on the surface and its interaction with the atmosphere. Using advanced radar, Veritas will map the Venusian surface with resolution about 100 times better than previous missions, allowing scientists to identify geological features as small as 10 meters, 33 feet. This detailed mapping is critical for understanding Venusian clouds because surface geology and volcanic activity directly influence atmospheric composition. Veritas will be able to detect active volcanoes by measuring thermal emissions and changes in the surface over time. When a volcano erupts on Venus, it launches gases such as sulfur dioxide into the atmosphere, which eventually transform into sulfuric acid in the clouds, directly feeding the acidic hydrological cycle we just discussed. Veritas will also carry an infrared emission spectrometer that can analyze surface composition through the clouds, potentially identifying evidence of recent geological activity that could be affecting the atmosphere. Beyond these two main missions, NASA engineers are developing even more revolutionary concepts for direct exploration of the habitable layers of Venusian clouds. One of the most promising is the concept of floating atmospheric stations, balloon-like platforms that could remain in the middle layers of the clouds for extended periods, possibly years, instead of the brief flybys or descents that characterized previous missions. These atmospheric stations would be equipped with instruments for continuous chemical analysis, meteorological sensors, and potentially even biological experiments designed to detect signs of metabolic activity in cloud aerosol samples. By remaining in the clouds for long periods, these platforms could observe seasonal cycles and other long-term phenomena that short-duration missions simply cannot capture. The most advanced concept for these stations is the so-called controllable Venus balloon, which could adjust its altitude to explore different cloud layers, using a double balloon system where an outer balloon contains helium for general buoyancy and an inner balloon can be inflated or deflated for altitude adjustments. The platform could navigate vertically through the habitable zone, selecting specific altitudes for detailed study. For more targeted exploration, small atmospheric drones are being designed specifically for the Venusian environment. These shoebox-sized autonomous vehicles would use small propellers for horizontal navigation, allowing them to move between different regions of the clouds to investigate localized phenomena of interest. A particularly innovative design is VAMP, Venus Atmospheric Maneuverable Platform, a hybrid between an aircraft and a balloon that could glide during the Venusian day, using solar energy for propulsion and float passively at night. This vehicle could cover large horizontal distances in the clouds, something a traditional balloon cannot do since it is at the mercy of the winds. These drones could be equipped with miniaturized instruments for in situ chemical analysis, including microscopic mass spectrometers and sensors capable of detecting specific biomarkers. Their mobility would allow them to investigate the intriguing UV-absorbing dark zones up close, potentially resolving the mystery of their composition. Perhaps the most ambitious of the mission concepts under development is a sample return mission from Venusian clouds. Although technically challenging, such a mission is not impossible and would be revolutionary for our understanding of the chemistry and potential biology of Venusian clouds. The concept involves a vehicle that would enter the Venusian atmosphere, collect aerosol samples from the middle layers of the clouds, and then ascend again to transfer the sealed samples to a return spacecraft in orbit. The main difficulty is not the collection itself, but ensuring that the samples remain unchanged during the return to Earth, since sulfuric acid droplets are notoriously unstable when removed from their native environment. NASA engineers are developing specialized containment systems that could maintain Venusian conditions of temperature, pressure, and chemical composition during transport. If successful, such a mission would allow much more detailed analyses than are possible with instruments sent to Venus, potentially including complete sequencing of any genetic material if Venusian organisms really exist. Future exploration of Venus is not limited to NASA alone. The European Space Agency, ESA, is developing its own mission to Venus called ENVISION, scheduled for launch in the early 2030s. This orbiter mission will complement DaVinci Plus and Veritas, providing additional data on the Venusian atmosphere and surface. Russia, which has a long history of Venus exploration with its Venera program, is also planning to return to the planet with the Venera D mission, which could include an orbiter, a landing module, and potentially even an atmospheric balloon to study the mid-altitude clouds. India and China have also entered the race to explore Venus, with the Indian Space Research Organization ISRO developing the Shukrayaan-1 mission and the Chinese Space Agency considering various Venus mission proposals. This broad international participation highlights the renewed global interest in our neighboring planet. What makes this new era of Venusian exploration particularly exciting is the growing collaboration between space agencies. NASA and ESA are already coordinating their plans for DaVinci Plus, Veritas, and ENVISION, ensuring that the instruments and timelines of the missions complement each other to maximize scientific return. This collaborative approach, rather than the competition that characterized the first missions to Venus during the Cold War, promises to accelerate our understanding of this enigmatic world. The data from these future missions will not only reveal secrets about our neighboring planet, but also provide crucial insights into fundamental scientific questions. For example, understanding how Venus's atmosphere evolved over time will help us refine planetary evolution models that can be applied to exoplanets, planets orbiting stars beyond our Sun. The implications for astrobiology are equally profound. If any of the future missions detect convincing evidence of life in Venus's clouds, it would be a transformative discovery that would dramatically expand our understanding of where and how life can exist. This would suggest that life may be much more resilient and widespread than we currently think, with important implications for the possibility of life elsewhere in the universe. Even if we don't find life, detailed study of the Venusian atmosphere will help us refine methods for detecting biosignatures on distant exoplanets. By better understanding how non-biological chemical processes can produce compounds that could be confused with signs of life, scientists can develop more robust techniques for the search for life beyond the solar system. As these missions approach reality, it's important to remember that the exploration of Venus is not just about unraveling the mysteries of a single planet. It's about expanding our fundamental understanding of planetary systems, atmospheric evolution, and potentially the prevalence of life in the universe. The mysterious clouds of Venus, which for so long have intrigued us with their chemical and physical peculiarities, may be about to reveal secrets that will transform our understanding not only of our planetary neighbor but of our place in the cosmos.